We are about to conclude this chapter, but we would like to mention a few other SparseLand-based algorithms that address the image denoising problem, just to show you the wealth with which one could bring this model to the application. In the past decade, we have witnessed a surge of patch-based algorithms, all aiming to treat the image denoising problem. These methods are substantially different from each other, while having one major thing in common, the operation on patches. Some of these papers chose to build on the above described algorithm and improve on it in various ways. Few others, still based on the SparseLand model, took a different way altogether. The concept of low rank, which was shown to be closely related to sparsity, has made an impressive entry to image denoising. Other patch-based work took a more direct path, using a learned GMM model or even working with the image patches directly. In this discussion, we mention few such attempts with emphasis on the sparsity-oriented ones. A discussion on image denoising cannot be complete without mentioning the BM3D, a brilliant work by Dabov, Foy, Katkovnik, and Egiazaryan. This is the paper presenting the block matching 3D transform, which was published in 2007, BM3D in short. For a long time, and until recently, this algorithm was considered as the best performing for image denoising. Let's present the core ideas behind the BM3D. This method exploits both the sparsity of image patches and the self-similarity property. Recall that we mentioned an algorithm by Mayral that has these two forces as well, and indeed the performance of the two is on par. Still, BM3D is different. Assume that this is the image to be cleaned, and these are few patches and their neighbors in the high dimensional space. BM3D suggests to gather these into 3D cubes and then apply thresholding algorithm on them, this way filtering all the patches in the cube together. Then they are sent back to their locations and averaged on the overlaps with their spatial neighbors. Okay, this was a bit vague. So here is the actual process that BM3D does. The following is repeated for every patch. Starts by finding its neighbors and pile them into this 3D cube we have seen. Then apply the thresholding algorithm on this cube, where the dictionary could be either the 3D HAR or DCT. So this comprises of a forward transform, shrinkage, and an inverse transform. Once done, put back these patches into their original locations and perform a wise averaging that prioritizes sparse representations. An important ingredient in this algorithm is the fact that the process is ran twice, both times on the raw data, but using the cleaned image in the second time to get an updated neighbors assignments. In the second round, the hard thresholding is slightly relaxed, something we will discuss later in this course. And that's it. The algorithm performs very well. For example, on the Barbara image we kept experimenting on, it gives 31.76 dB, half a dB above the K-SVD denoising algorithm. We move to a different algorithm altogether. An interesting paper suggested adapting the shrinkage curves to the image. In the early work of Gullerius, we used the DCT and the hard thresholding. When we moved to the K-SVD denoising algorithm, we focused on using a better dictionary. Well, now we may ask, why should we stick to the hard thresholding? Perhaps there are better curves to be used. This is exactly the idea in this work from 2008 by Helor and Shaked. We are still operating on patches and still using the thresholding algorithm architecture while questioning the shrinkage to be used. Here is the basic idea behind this work, and as you can imagine, the main novelty will be in formulating this problem into a pleasant optimization task. Take a look at this expression. We have a set of clean patches, pk0, and matching noisy ones, pk. Our goal is to design the thresholding parameters, theta, such that the denoising process on pk will get as close as possible to the clean patch, pk0. Who are those theta parameters? The idea will be to describe the curves as a linear combination of basis functions of some sort, and then the combination coefficients are the parameters to be found. The beauty in this idea is that all this turns into a lovely and pleasant least squares problem with respect to the unknowns. Obviously, we should train on a set of patches and test the resulting curves on other ones. Another important feature of this work, we will be using the 2D DCT as the transform, and each of the n squared coefficients will get its own tailored curve. We will not dive into the formulation and the optimization and turn to show the results. For patches of size 5 by 5 pixels, these are the 25 shrinkage curves that were found as optimal when trained on patches taken from the image Lena. Notice that the low frequencies are hardly touched, while high ones are damped hard. Using this approach for bigger patches of size 12 by 12, we get to 29.23 dB denoised image. Nice, but we have seen already better performing algorithms. Could we improve this scheme somehow? The answer is yes, and this is also described in this paper. We have optimized the curves to lead to the best denoising on patches, but we did not take into account the fact that there is an averaging stage afterwards. A better method will optimize the curves to get the best final image after this averaging. And here it is. Still a least squares problem, but somewhat more involved, and the results jump by 0.5 dB. Look at these curves. Some of them are reversed. This leads to some sort of sharpening effect that seems to improve the overall performance. Let's say a few words on denoising video, image sequences. All the ideas we presented in this chapter could be brought to serve video. Yes, we can always filter one frame at a time independently, but this is far from the best we could do. The key idea in migrating to image sequences is to exploit the redundancy between frames in order to get both faster and better denoising effect. And indeed, along these lines, we have seen a series of attempts to remove noise from video, starting with the non-local means, which we will discuss in the next chapter, moving to the BM3D, and even generalizing the K-SVD denoising method. Let's talk about the last of this, the K-SVD method. Recall how we denoised a single image by working on patches, training a dictionary, and sparse coding the patches, and then merging them back by averaging. We can improve on this by propagating the dictionary from one frame to the next, and thus save a lot of computations. After all, since adjacent frames are similar, the dictionary remains very much relevant. Secondly, one could work with small 3D patches instead of 2D ones, and thus exploit both the spatial and the temporal structure that exists in these patches. Beyond these, an interesting observation is that we no longer need to rely on motion estimation. It is absorbed by the dictionary atoms that are 3D patches as well. Here are two examples for the denoising performance that can be obtained. In both, we show the original video and the noisy one, and then present the denoised result.